Good evening, everyone, and welcome to the Vacuum Transport Seminar. We have two interesting talks today. The first is from the side of Delft Hyperloop, and the second one is from Labeled. And just as a quick introduction or reminder again for the audience, we use this tool called slido.com, where you can put all your questions during the talks. And then after every talk, we will have a short interaction round where we ask the questions to the speakers. So feel free to go to slido.com. Daniel just put it into the chat. The event code is VAC Transport Seminar, and then we can collect all the questions on this website. So now let's jump right into it. I would quickly like to hand over to Lucas for a short, more detailed introduction of our first speakers. Thank you very much.
Thank you very much. Well, I'm very delighted to announce our first talk here, Hyperloop Safety and Security Analysis from Delft Hyperloop. I think I've met you, Twan, already in Brussels, but I think I haven't met you, Sarah. We're probably going to meet EHW then next year. So I'm very happy about that. I'm very much looking forward to your presentations. We've seen all the great work you've done on Hyperloop Connected on the website and all the reports that are there. So I'm very happy to have you now go into a little bit more detail to explain to us what we are looking at here.
Yeah, thank you for the opportunity to speak here tonight. Like Lucas mentioned, we're Twan and Sarah, and we're going to talk about the research that has been done in the past by our team. But I will first start with some general information about who we are, because it's like most of you probably already know us from the conference, but just in case if you do not know. This is us. We are a team of 39 highly ambitious students. Most of us take a gap year to work in this team. We're called a TU Delft Dream Team, and we work 1 year towards a model. We have like different departments. The engineering department works on this model, integrating different subsystems into a working path, and with that path we're going to participate at the EHW, which is the Hyperloop competition, and we are also part of that competition, but not with the path, but with research that we perform. So we are working 1 year towards the EHW, and we're working on 2 research papers. And this is who we are. Like tonight, we represent scalability. That's our department's name. And we are with 2 more. And the mission that we have is that we want to make an impact by exploring a realistic implementation of the Hyperloop system. So, like I said, we are the research department of the team, and we're working towards the realization of the Hyperloop system. So the goal is to write the 2 papers who are going to participate in the competition. One paper is focused on a socio-economic topic, and the other paper is focused on a technical topic. So research has been done in the past by our team, because every year the team switches, so all students are replaced with new students. So we're going to present the work of a team in the past. And that's about safety and security. It's a very important topic as it's a new technology, and it's possibly filled also the path with passengers, which makes it even more important to have thought the safety and security really through. It's also very broad because it should answer every question of what happens if. So what happens if there is an illness? What happens if there's an explosion? What happens if, well, you can fill it in for yourself. There are a lot of possibilities. So what we will discuss tonight is a general safety analysis and security of the Hyperloop station. That's I will do the first part and Tom will do the second part. So safety. What the DA Delft Hyperloop team did was this approach, which is visible on the slide. It's like quite a common method to use when you go through a safety analysis. And I will go through each part to explain what has been researched. So we start with the safety performance and the safety target. So what Delft Hyperloop did, they wanted to have this safety analysis, but for that to be done, you need the safety vision. So the safety vision states the European Hyperloop system shall have at least the level of safety of European commercial airlines in terms of passenger fatalities per billion passenger kilometer. So, but yeah, it's because it's a new transportation mode. A lot has been compared with what's already known. So in this case, the vision is compared with airlines because it's like the most, it has the highest safety of all transport means. So that's why the Hyperloop also aims to be that. This is the safety framework that has been used. It's every part kind of shows a way of how to work with the safety and what needs to be done. So you have like different aspects. Proaction means that an unsafe situation needs to be prevented, and how that can be done is through that circle, through prevention, through preparation, through mitigation, through intervention, to aftercare, and through evaluation. And by working with that cycle, you can kind of ensure the safety. So from the safety vision, a safety goal was defined, which states the passenger fatality per billion passenger kilometer will be 0.06 or lower. The 0.06 is also again compared with the airlines because there is the passenger fatality is 0.06. So that's what Hyperloop should aim for. Now about emergency scenarios. So there are quite some. The first one is fire in the pot. So this can be due to like mostly the systems heating up, for example, the batteries. So yeah, that needs to be taken into account. Vehicle collision is the next one. This can, for example, be the case when the braking system fails or propulsion system fails. Yeah, there are multiple reasons for this to happen. Sudden stop of the vehicle or vehicle stranded between stations. Yeah, what should happen in this situation? Passenger injury or illness, breach of the pressure vessel due to, for example, an explosion, and damage to the pressurized tube, for example, because a vehicle encounters the tube for some reason. So yeah, we're going to include quite some aspects of the safety approach in the next slides. First of all, fire safety. This is one of the emergency scenarios I just stated. So it's mostly about the areas with atmospheric pressure. Within the tube, there isn't a lot of air, so the chance of getting a fire is yeah, quite low, but it's still possible, so it should be taken into account. But within the report, they focused really on the atmospheric pressure areas. So they looked into the required safe aqueous time. This is the time you need to be able for the passengers to safely evacuate a fire situation. So they thought of that to their analysis, and they came to this conclusion. There are multiple ways to control the fire. The first way is to prevent it through flame retardant materials. However, this is not always a way to make sure that it doesn't happen. So when there is going to be a fire, you need to be able to detect it through multiple ways. You can use smoke detectors, for example. When there is fire, you need to suppress it. For example, with what's visible on the slide, you have oxygen deprivation. This is of course not done in a passenger area, but more in the systems area. An helium gas system is used for the batteries, and fire extinguishers can be used by the passengers because the pods are automated, so the passengers need to be able to know how to use those, but they will be available, of course. And compartmentalization, which means that the systems and the passengers are divided from each other, so that's for example, the oxygen deprivation is possible. So, like I said, it's advised to automate the pods because it prevents human error in operational critical functions. What's visible on the slide are the ways that the pod can be automated and also advised through the report. So you have the positioning of the pod, the maximum speed, the deceleration and acceleration, and the vehicle stability. So also the communication is discussed. This is very important as the pod is automated. It needs to be completely able to function on its own. So for that you need a lot of communication systems and so connections as well. So there are quite some requirements to this. You have the peak data rate, which is dependent on the amount of passengers. Like it states, it's 2.5 Mbit per second per passenger. So for a whole pod, like dependent on how big your pod is going to be, the peak data rate also changes. The handoff success rate needs to be more than 99.9%, so it kind of needs to be perfect. And the handoff means the process of transferring an ongoing call or data from one channel connected to the core network to another channel. And then the cell range, this is compared to high-speed rails, which needs to be between 1 and 12 kilometers. And finally, the latency for critical services needs to be smaller than 50 milliseconds. This is only for the critical systems. So for example, for the internet for the passengers, it doesn't really have a big latency. It doesn't really matter that much for that. There are also service requirements. Passengers always need to be able to be in contact if needed with emergency post. There should be real-time monitoring within the pods so that it can be known what's happening, how the passengers are behaving, stuff like that. Internet for the passengers, and a separation of network is also advised as it's more safe. So the propulsion system needs to be separated from the levitating system, for example. So for all that communication between the pod and the tube, that can be quite difficult. So they went into the possibilities there, and they found that the light fidelity communication system is the most preferred. So a binary signal is made from the flickering of LEDs, and the LEDs are able to function within the vacuum environment and within certain distances from each other. So that was very useful. And what is visible on the slide is a possible design, or more like an explanation of how this communication works. So you have the internet and the server, and the control center and the control data, which influence the base station, and the base station again makes sure that the LEDs are flickering in the right binary signal, which makes sure that there can be communication. They also thought of ways for passengers to evacuate during emergencies. So there was like a difference in impact and brick and wall emergency. Impact means that the functioning of the system still works, but the passengers are in danger, for example, due to a passenger being aggressive. And the brick wall emergency is when the functioning of the system is failing and the pod itself cannot reach a station or a safe haven. So they thought of that. So the safe haven is one of the possible concepts. It's found in metro systems as well. It's kind of a station within the infrastructure. And there are multiple ways to do this. You can have like an internal safe haven or an external safe haven. The external safe haven does include like extra infrastructure, but it is more advised because the operation as itself, it doesn't have to stop if one pod fails. So it kind of stands besides the tube and other pods can still pass. So yeah, that would be more preferred. And there's also been thought of in-tube evacuation. This means that passengers are able to walk across the track due to a pressurized environment, which can be obtained using like doors within that tube, which so kind of compartmentalize the whole infrastructure. And the most advised option was a combined evacuation. So like we saw here, when there's a brick and wall situation, the pod cannot reach a safe haven. So then the in-tube evacuation is preferred, but with in-pod emergencies, the safe haven does work perfectly. So yeah, it depends on what you want, but as we said, the safety vision is quite high, so a combined evacuation plan is preferred. And then we're going to look at the safety packages or the safety measures, because like there was a final opsomming. Sorry, sometimes my English doesn't. Do you know?
I'm lacking now too.
My English is lacking. All right, but there was like this overview of safety measures. So we have safety education, which is like most preferred an interactive learning experience. Like for example, within the airplane, you have the stewards who are showing what you need to do when there's an emergency. That works pretty well. It has been researched a lot, but that's not possible in a pod. So this interactive learning experience needs to be done in another way. For example, using interactive screens. So that's would be very useful. Track sections, when a power system fails, it should be able to continue working. So the sections between the track is very useful. And isolation of subsystems, so that they, when they fail, do not contaminate the others. Or so, for example, the batteries need to be stored separately so that the halon gas, when there's a fire, can be put into that space and the fire like extinguishes. That would be the most preferred option. And finally, a redundant subsystem design would also be preferred. This is, however, very costly. So like an overview needs to be made of the different subsystems and to look into which subsystem needs to be most redundant. But yeah, so that comes with cost, but is also like very much preferred. This was a lot of information they made all that information into, besides those safety measures that I just showed, into safety packages. But first I'm going to discuss risk assessments, because they also researched the different risks that come to be in a Hyperloop situation. So what they did is they looked into the likelihood of different failures. Yeah, that came from occasional to frequent, and to not really not really likely to happen. There were also impacts. So the impact is dependent on the type of hazard and the severity. That was created for different failure modes, and the likelihood and the impact together went to a risk score, which is put into an impact likelihood graph, which shows which failures should be really looked at, and which failures are quite okay and aren't really likely to happen, so don't really need a lot of attention when you are going to make this safety approach for the Hyperloop. So then I'm going to discuss the safety packages that came out of the safety measures. There were 3 safety packages. The recommended version, which is needed to achieve the safety targets, and it includes things like internal aid and improved perceived safety, stuff like that. I didn't discuss the perceived safety, but it is a way for passengers to feel more safe in the environment that they are in. So stuff like claustrophobia are taken into account. And there is an additional safety package, which isn't really necessary to achieve the safety package, but when included does improve the safety with a lot. So things that are in here are the redundant subsystems that I discussed during the safety measures, and the safety education. And there's a maximum safety package. To be honest, it's too much. It's not really necessary, but if you're really going for all out, then you can include this safety package. And then Twan is going, there will be time later for questions if you have any, but first the security.
Yes.
Maybe we can ask you, Twan, to speed a little up, because
Yes, I saw the clock. I will
I'm
be a
sorry.
bit faster than Sarah.
Sorry, Sarah.
Our previous predecessors have envisioned the Hyperloop system as a turn-up and go system, as to keep the speed of the travel. And on the other hand, you want the Hyperloop system to be safe. It's quite an attractive target for example, terrorist attacks, because it is both very fragile and international travel. So this poses security requirements, and these are 2 quite conflicting interests, and therefore in this research threat and vulnerability risk assessment has been performed, and I will go through that very quickly. This is an overview of the research that they have performed. So first of all, they analyzed which assets are present at a station. So for example, the passengers, but also the tube itself. Then which threats could be considered on a station, so what could possibly go wrong. These are then combined into a huge matrix to see which threats are relevant for which asset. Then of each of these combinations, the criticality, each of the assets, the criticality is determined in the criticality assessment, and also the vulnerability to each threat and the consequences of each threat occurring on this asset is assessed. And all these are then combined into a risk score. Then finally, possible measures are considered. What could we implement in a station? And then how does this influence all the risk scores? And based on this improvement of risk scores due to several measures, some measures are actually recommended. So first of all, I'll go quickly through the assets that have been considered. So we have, of course, the passengers, the pod, but also the fire suppression system. You want to be sure to extinguish a fire in case necessary. Don't forget the structural system, so the station needs to be structurally stable. And all these other systems, for example, the airlock system, which is not unimportant in a Hyperloop system. I'll go quickly through that because it's quite a summation. And also for the threats, what could possibly go wrong? Someone could bring a bomb. That could be, for example, a suicide bomb, but also a luggage bomb could happen. This is what happened at the airport in Brussels. Another thing that could go wrong is an armed attack, or an attack with chemicals even, although that's not very common these days anymore, but you don't want it to happen anyway. Criminal acts are way more common, so for example stealing, and arson is also not very preferred. I think finally we have an attack on a control room, which is quite more modern. So that could be hacking the system. That could be quite catastrophic as well. So then we'll continue into the matrix, and here you can see how each thread relates to each asset. So for example, an attack on a control room does not really influence the maintenance equipment. In this way, our predecessors have determined which threads are relevant for which asset. And thereby they have investigated each score for the criticality, vulnerability, and the consequences. So the risk can be determined via this formula. Risk is in general the probability of something happening multiplied by the consequences. And in this case, they have included the criticality of the system, which is the factor C. And this basically means how critical is the system for your, how critical is the asset for your system to still operate? For example, you need your station to be accessible for emergency services. And this is only relevant for a certain asset and does not is not really influenced by the threats. Continued in the formula, you can see a summation over I until N, and I is a thread and N is the number of threads that are relevant for a certain asset. And for each of the thread, the vulnerability is determined. So how vulnerable is a certain asset, for example, to a portable bomb. And then it is multiplied by what would happen if the bomb would actually go off, which is the effect or the consequences of the threat on the asset. So when this is determined, we will have the risk scores of all the assets in the station, and they are listed in this slide. And as you can see, the passengers, the pod, the airlock system, and the personnel are the most vulnerable, no, most at risk, not most vulnerable. So those need to be protected, and we will look into safety measures for them. Yes, we will do that now. Some of the safety measures that have been seen in other modes of transportation are these. So baggage screening and passenger screening, we all know it from flights. We of course need personnel for that screening, but this personnel, the security personnel, also has to be screened in order to make sure that they are not a threat themselves. We could impose identity checks, which is performed in international travel already, but not so much in national or Schengen travel. It might be good to look into how that is allowed within the EU, for example. Trained dogs are sometimes used. I once had that. I walked out of a flight and there was like 2 dogs sniffing everyone whether they had drugs. But they could also do that for bomb traces, for example. But there's fortunately also trace detection systems available for that. Security staff also needs to be trained for to be able to prevent threats, but also to be able to handle them. So in case someone attacks, what should you do? How should you handle that? More common measures are, for example, the CCTV, closed circuit television, which is basically security cameras. And this could be combined with artificial intelligence in the future to recognize how people behave. and whether that could be a threat. Based on this, they have reassessed the risk scores, and from this they came to 4 recommended safety measures, which are the following. Screening of people and luggage, so the same as at an airport. Also screening and educating the security staff. Additionally, they would like to add CCTV security cameras, preferably combined with artificial intelligence in the future. And they would like to impose identity checks, but they put a little side note that it might be difficult within a single country. When you travel internationally or outside of the Schengen area, you would of course automatically check identities, which helps greatly to check whether people are not on a blacklist or something. So that was quickly our safety discussion. We now have time for questions.
Well, thank you very much for your great presentation. I would maybe propose to ask the question like after both of those presentations. So you've got like 20 minutes to listen to Sebastian now, and then we'll come to all of the questions together. I've just made myself a screenshot of all of the questions so that we can look at them afterwards. I've already posted something in the chat that there's more from your full safety and security analysis report on hyperloopconnected.org. And we'll come to your questions in a second. I would just want to introduce now Sebastian Rosensteiger. He's from Leibold. He's an application engineer at Leibold. We've been with your company in October together with TU Munich. We've had a great presentation on all the challenges for a vacuum system that is integrated to a Hyperloop transportation system. So we are very happy to have you here and bring all those facts to us, bring all those challenges to us and explain them to them. So the floor is yours, Sebastian.
Yes, thank you, Lucas. Let me share my screen. So, not really used to using Zoom.
Seems perfectly fine.
So I leave my video. I just say hi quickly to the camera because my internet connection is not really good. Hi, everyone. So it's probably better for the audio if I leave it off. So welcome everyone to the Hyperloop webinar. So as Lucas already said, he and his team visited us in Cologne about 2 months ago, where I held a longer talk about Hyperloop challenges from a vacuum perspective. So, and this is now, you could say, an excerpt of this talk about 2 of the topics I presented back then. So, I'll have 2 topics here, which I will explain. The first one is basic design of a Hyperloop pump system. So how do we select pumps and the pump layout for a given Hyperloop task? And then the second topic I'll talk about is about pressure shocks of passing pods. Okay, let me start with the first one, design of Hyperloop pump systems as we do it. So basically, when we talk about Hyperloop pumping systems, we have 2 major operation points which we have to think about. So at least in the general the pump down of such a tube or of a load lock chamber. And then the second operation point is just maintaining operation pressure. So being it 1 millibar or 10 millibar, which is basically just pumping away leakage. So you'll never get these tubes completely airtight. There will always be a leak, and these leakages have to be pumped away to maintain the pressure. So for the following, let's talk an example tube or a section of a tube with a length of 1, diameter of 4 meters. Let's just say operation pressure is 1 millibar and we have a total leak flow of 200 to 400 SLM. So it'll be between that. These are arbitrary values, but they are not completely off from what we've seen so far in the pump systems or the applications we've seen so far and for which we've supplied pumps. So for these operation points, I have to get rid of the video line here because I can't see anything. So we have different options. Starting from the left here, the easiest option would be just to have a lot of 4 vacuum pumps, so pumps that compress air towards atmosphere, and just use as many as you need to pump away the leakage at 1 millibar. So for this given example tube, we would then come to 24 of these dry screw pumps DV1200, which are actually 2 pumps in one big box. So in the end, this would be 48 pumps, quite a big number of pumps. So then we can also go a second route that would be having something like here, such a backpack solution. So you have a roots pump, which is just a pump that compresses about a decade in pressure. So it would be compressing from 1 millibar to roughly 10 millibar here. And then you have the 4 vacuum pumps again. So by just compressing the leakage from 1 millibar to around 10 millibar, for this you would need 4 of these big blowers, and then following 4 of the 4 vacuum pumps. So these would be directly stacked. You would directly stack them on top of each other. Then you would have 4 pumping system, and in total 4 of the big pumps, and then 4 of these boxes, which would be 8 pumps. So in total, this would be 12 pumps compared to 4 to 8 pump units here on the left. So same pumping speed at 1 millibar, but just a fourth of the pump. Or you can go even one step further and have a multi-stage pump system. So here with 3 pump stages. So where you would have 4 of these big roots blowers compressing about a decade in pressure in the first stage. A second one, a second stage here with just 1 of these roots blowers, again compressing about factor 10. Here 1 DV1200 pump at the bottom. So 1 of these big box pumps, so with 2 pumps in there. So in total you would have 4 in the first stage, 1 in the middle, so 5, and then 7 pumps. And they all these 3 vacuum systems have the same pumping speed. So it's a clear thing. You would go for the pumping system on the right, but it's not always that easy. So let's just have the diagram here. Here we see again these 3 pumping systems and you have plotted here the energy consumption, the leak flow here on this, let's call it y-axis, and on the x-axis we have the 3 different pumping systems. So there you can see energy consumption, of course, with 48 vacuum pumps, although you compress the same amount of gas with each pump system, is much higher with just the system that has these 48 4 pumps. If you introduce 1 root stage, so this would be here the second system here, the second row, you can see that the energy consumption is much lower, and the amount of energy that is consumed by the roots pumps is not really high. So if you have the multi-stage root system, you can see that you have a much lower energy consumption. Of course, you reduce a lot of pumps, and by that the energy usage. And now you have the blocks which you cannot really see, which are shaded a bit. This is if you would optimize these systems for a given leak flow. So of course, for 400 SLM of leak flow, you would need more pumping system than you would need for 200 SLM. Sorry, a quick. Someone was banging on the door here. So you can see regarding energy consumption at these low operation pressures, it would again be a no-brainer. Why would you need these bigger pumping systems here with just 4 vacuum pumps? But let's have a look at pump down performance. So you want to pump down a given chamber. So here we have the tube of 1 kilometer, and for meters in diameter. So how long would you take with these pumping systems to pump down these tubes? So, and you can see here again, the first block here is the pumping system, which is consisting of these 48 4-vacuum pumps, dry screw pumps, where you can see, depending on leak flow, you'll be between 3 and 4 hours at your target pressure of 1 millibar. So starting pressure being atmospheric pressure. If you have the backpack solution, so roots blower on top of the 4-vacuum pumps in a 1-to-1 configuration, you'll be around 10 to 11 hours. And if you have the multi-stage root system optimized for the flow at 1 millibar and optimized for energy consumption, so not a lot of pumps, good usage of the energy, but they lack the 4-vacuum pumping speed. So the initial pump down where these roots pumps are not really efficient because they cannot pump at high delta P. So basically only the 4-vacuum pumps, the boxes on the bottom, are working here. And you can see it takes much longer for a pump down. So here is a diagram where you can see the pumping speed curves. So the pumping speed each of these pump systems has at a given pressure. And then you can see that the one with only the 4-vacuum pumps has a very high pumping speed over the whole pressure range, so from 1000 to 1 millibar. And the two other ones, you can see that the pumping speeds drastically increase toward the 1 millibars, and you hardly have any additional pumping speed from the roots pumps. So although all fulfill the pumping speed requirement at 1 millibar, you wouldn't take all of them for a load log system, for example. So for a load log system, you would lead the pump system with much more 4-vacuum pumps that can pump down these chambers really fast. And for just the operation of the tube, so having the pump running at low pressures all the time, you a multi-stage root system, because these pumps, the tube for itself, you wouldn't pump down too often, or you shouldn't pump down too often, because it'll take much longer, or you'll have an inefficient pump system. Yeah, so you can see pump systems for these applications are always a compromise between what you want to reach, so between pump down and operation pressure. And you can also see that if you are using load logs, you should definitely think about using dedicated pumping system and not try to use the pump systems you have to maintain your operation pressure for pumping down the load logs, because they're just not as efficient at pumping at high pressures. So with that, let's come to the second topic, which uses a bit of what we've talked about so far. So a big point in discussions when talking about Hyperloop aerodynamics is the blockage ratio. Oh, there's an L missing here, sorry for that. Blockage ratio is the ratio between the diameter of a pot divided by the diameter of the tube. So usually we're talking about round objects here. Of course, there might be variations of this. There's an extensive number of studies, most of them numerical, that describe the effect of different blockage ratio on pot aerodynamics. I'm not going into detail about that here. Aerodynamics, you might know much more about this than I do. But not only the pot sees a pressure shock or a difference in around itself, which will for sure affect the drag it sees, but also the surroundings of the pot will see this pressure shock. So, and of course, if you have vacuum systems connected to such a Hyperloop tube, these vacuum systems also see a pressure shock. So what happens now to a vacuum system if it sees such a pressure shock? So it's not a simple answer here, but for sure there's a risk depending on the pressure gradient, and the pump configuration. So we talked about this. You could have either just these 4 vacuum pumps as a very simple system, or a one-to-one system, or one of these multi-stage root systems. So depending on which pumps you use, you might have high will also compress such a pressure shock. So what might be a possible risk? If you have these pressure shocks coming into such a roots pump, you will also roughly multiply the pressure of this pressure shock by the same ratio as you have normally. So if you say you have then the pressure shock will also be compressed by a factor of 10. So, and this can harm the motor shaft, bearings, or other parts of the pump. The extreme would be venting such a pump. So just having from operation pressure to atmospheric pressure at the intake, then you will have atmospheric pressure at the intake of the pump, and it will be multiplied with factor 10, and then you have 10 bars of pressure at the intake of the following vacuum pump. It's not very likely, but for sure the vacuum pump would be destroyed by that. So, but usually operation pressure is rather low. For the example before, we used 1 millibar. It might also be 10 millibar, but it's very unlikely it will be much higher. And you'll have additional volumes in front of the pump. So at least a bit of piping, which will dampen these pressure peaks. So here we've made a plot where we said, well, what might be the effect of such a pressure shock? So, and this all depends on how big is such a pressure shock. So we used here an arbitrary value of 8 millibar, depending on blockage ratio and pod design. This might be higher or lower. And then you can see here from the plot, depending on the inlet pressure here, which is plotted on the y-axis, and the compression ratio of the pump, of the first pump, you can see different variations. So if your operation pressure is really, really low here, so below 0.5 millibar, you could say, no matter how big the compression, there's hardly any risk for the vacuum pumps. If we're going higher in pressure and depending on the compression ratio, you might see a light impact. So this will be the frequency converters of the roots pumps will slow down the pumps because there's just a high delta P. So the pressure differential is so high. If it gets even higher, you might see long-term effects. So that bearing life is not as high or something like this, or at really high values. But here we're talking about above 100 millibars of inlet pressure. Such a pressure shock would most likely kill the 4 vacuum pumps. So any pump that would follow such a roots blower. So this is a very theoretical plot, but how would it look like for a realistic pumping system? So in here we have performed a simulation with our in-house simulation software. You can see here we have the main tube. Can you see my mouse? I don't know. Can someone please confirm?
We can see it, yeah.
I can also use the laser pointer here. Okay, so we have the main tube. We have a such a operation leakage system, you could say, such a multi-stage root system connected to the tube. A short bit of piping, the first stage, a manifold between the first and the second stage, and again a manifold between the second stage and the 4 vacuum pump. And then you can see we already have additional volumes which will dampen these pressures. And let's see what influence we'll have on the operation pressure of the system. So of course there is a variation in there's an effect of the duration of the pressure shock. So let's see what happens if we have a pressure shock of 8 millibar for just 0.1 of a second. So here we have each of these teeth, you could say, is one pressure shock. And what will happen is we have plotted here the rotation speed of the roots pumps. So they're running, the first stage is running at 70 Hertz and the second stage is running at 65 Hertz. And you can see, if you don't consider any pipe works, because of the high delta P, the rotation speed drops down. And of course, with the rotation speed of the pump, the pumping speed drops down. So in the end, with having multiple repetitions of this pressure shock, here we have 30 seconds, you would see the rotation speed will be lowered over time, and the pressure of the system will be lower. If we consider the pipe work here, just for the 0.1 second pressure shock, there's hardly any effect. So you can see maybe the rotation speed drops from 65 to 64 Hertz overall, but we don't see an effect. But now what happens if these pressure shocks are for a longer time? So longer pots, different configurations, then you can see that without pipe work, the average rotation speed of the pump system will be around 61 Hertz and maybe 62 Hertz with pipe work considered. So you can see there is a notable effect, which would mean the pressure inside the tube would be slightly higher because the leakage is not pumped away as fast. So, and what we did not consider here is the increasing pressure, which would of course then also increase the pressure shock. So there would be a slightly higher pressure shock at a higher intake pressure, so which would make this effect even worse. And as a last simulation we did, what happens if you have 1 second pressure shocks? Okay, I acknowledge these are rather long, given the speeds we expect from the pots. A 1 second pressure shock would be very long, but you can see even with pipe work here, the rotation speed of such a system would drop below 60 Hertz. You would lose, and even here now you can see that the rotation speed of the first stage drops. So you would lose between 10 to 20% of your suction speed, which would then result in a much higher operation pressure. So although you wouldn't think about it, that such a pressure shock from a passing pot has an effect on the vacuum system, it has to be mentioned. And if we design such a system, we need for a Hyperloop, we need such values. Or such a system, or to factor in some additional margin, so we are not at the brink of losing suction speed with these pressure shocks. Okay, thanks for your for listening. So questions? I think I hand over to Lucas now.
Well, thank you very much for that great presentation. I'm loving to hear about those challenges. Well, I don't love that we have those challenges, but I love to hear about them and see that somebody's thinking about them.
Maybe I can just say on the last presentation there was said likeliness of failing vacuum pumps, the likeliness of 4. I think it's much rather a 2 or 1. So it's not very likely they'll fail if you use our pumps.
I just wanted to ask that, like, if the pressure shock is really that long, so if that really will have such an impact on the whole system itself. There's probably some people doing aerodynamics that could tell us how long those pressure shocks will be, rather than the 0.1 seconds or the 1 second long pressure shocks. Well, we have a lot of questions here on Slido, so I'll start with you, Sebastian, here then first. We first have a question that is more general, but then I'll follow up with a more specific question. So they say, what are the current research optimization fields of vacuum pumps, and what is Leibert currently looking into? And then the second would be, which design would be a Hyperloop specific design, which follows when you want to go to a final pressure level at around 1 millibar. So a pump that doesn't reach those very low pressures that you can reach with the setups you have right now.
Okay, so at the moment, I don't think anyone is specifically designing vacuum pumps for Hyperloop. So from a vacuum perspective, Hyperloop is not a big challenge because it will be air. So of course it will be a lot of air, and there will be huge pumping system, but it will be air. There might be a little dust. There will be some moisture, some water vapor. But as we're talking about rather low pressures, from a vacuum pump perspective, this is not really tricky. So I'm pretty sure it will always be dry vacuum pumps. So you don't have, or you will have high maintenance intervals. You don't have oil as a medium that needs to be exchanged all the time, or big amounts of oil. And for sure, if there's bigger opportunities, there will be Hyperloop specific pumps. So these will be not as intricate as the pumps we currently use, probably. So will be reduced to the features that are needed. So, and then maybe there's even a specific specializing between load lock pumps for Hyperloop and pressure maintaining pumps. So if you know,
so
a pump is
an energy efficiency level that you're looking into.
It's energy efficient, and it's also features. So for example, you have purge gas, so which protects bearings on either side of the screws, but you wouldn't need intake or inlet purge for a pump that is just for maintaining pressure. That's constantly working at one pressure. You wouldn't have this. So it would be probably for some parts stripped down versions of pumps. But regarding pumping principles, I'm pretty sure it'll stay with dry compressing screw pumps as we use in these 4 vacuum pumps, so these boxes I've shown, and then paired with root blowers just to decrease the amount of gas that has to be pumped.
Oh, great, thank you very much. I have one more question. I just want to tell everyone from the audience, sorry if they have to get to a meal or something that they have scheduled right now. But we'll just record those questions, which I left also for the YouTube channel, so that everybody who's watching and interested can then look those up as well. Then we have one more question here on Slido, which more in a general Hyperloop perspective. So I don't know whether you want to answer that. So it says, in your opinion, when considering the overall energy consumption, drag, pumping, energy, and so on, what kind of ideal pressure level inside of the Hyperloop tube are you right now seeing from research and from all your partners you're working with?
I don't think we can really comment on this. So with all the people from the Hyperloop community we've talked so far, there's really a broad spectrum between 1 and 100 millibars, you could say. So, and there's lots of different simulations that have to factor in a lot of stuff. So it's hard to say. Of course, if we're talking about leakage, same amount of leakage at 100 or 1 millibar, there is a factor 100 of pumping speed also in there. So of course, with decreasing pressure, you'll increase the amount of vacuum pumps or of pumping speed you'll need. But well, we've asked the same question, where will it be, several times, and is it really, from an aerodynamic point of view, worth going from 10 to 1 millibar? So I don't think there's a definite answer out there yet.
Yeah, I guess.
But maybe you know more.
I think the biggest question there is what kind of blockage ratio you will have compared to the pressure. I think that's the biggest thing you have to weigh one or the other. And then it's what kind of more costs do you have when you increase the tube by, for example,
and you will have more leakage.
Diameter. You will have more leakage. You will have a bigger tube. You will have more costs. Will it be $1 million per kilometer more? How much will it be? So I think that's all compared to the pressure levels there. So I think somebody really has to do a really deep dive into that analysis there. Well, thank you very much, Sebastian. We are very happy to have had you here in seminar, and I will just continue with a few more questions here for Delft Hyperloop to also get those in here as well. there we have
Go ahead.
Perfect, you're still there. That's good.
Definitely.
Well, the first one we have is how much papers do you have taken into account in publishing? I've just also put in the chat the resources for your reports. They are on hyperloopconnected.org, and I think there's also some sources in there, so everybody can check those reports. And then there's the question, how much have you taken into account what's also happening at standardization level, European level? What kind of sources have you taken on? Who are you collaborating with when you're doing those reports, for example?
As we have not performed the research ourselves, I'm not quite sure whether they had a lot of contact with, for example, the European Union and standardization. But the security report is now from 1.5 years ago and the safety report from 2.5 years ago. So I don't think they already involved a lot of the standardization.
Yeah, I think so too. I think it just really started. And I think those, whoever asked that question, I think those answers might not even be out yet. As someone who's actively participating there, can say that some of the papers are just being published at national levels for review. So the next one is, do you categorize the scenarios you have shown into actively induced damages and passively induced damages to like separate the safety and security a little bit?
Wait, is there a question how the why there was a separation between safety and security?
Yeah, like, did you actively categorize them? Did you think about which ones are for system design and which ones are more for security design that might not be in standardization and everything?
Yeah, okay, I understand. Like Ton said, the safety report is from 2.5 years ago, and the team after that report came out, there also was a new team, and I think the team read the report and thought, oh, there can be a lot added to this report through the security of the station. So that's why they went into depth on that. So that's why there is a separation there.
Yeah, I think it's good to have separation.
I think the safety framework was meant to be more general, and then they suggested to dive into security at stations as well.
No, right. Then there's one more question towards the safe havens. Have you analyzed what a good size of the safe haven would be? So when it's inside of the tube, or would it even make sense to have such a small safe haven if it's probably located close to where pumps are, where infrastructure is, where you can access the tube? So does it really make sense to have a safe haven inside of the tube, and be it very small, or should it be very large, like 10 kilometers?
The difference between the safe haven, the internal safe haven, so in the infrastructure, and the in-tube evacuation is actually quite small. So that's why they recommended to do the safe haven like outside the infrastructure. But if it's chosen to be implemented this way, so inside the infrastructure, it's recommended to do it as an in-tube evacuation. So with through compartmentalization of this infrastructure, so that the tube can get to atmospheric pressure and people can get out.
A specific location, yeah, great. Like one last question we have, and then we'll wrap up the seminar. Which literature have you referred to when defining the requirements for communication with the cell ranges, F ratings, emergency scenarios for oxygen levels and fires and so on?
As we didn't perform the research, we are not sure, but we work with a lot of experts, so we probably contacted them for that information. But I can, if someone really wants to know, I can for sure look it up and contact the past team members so that I can come back with a more detailed answer.
And it should also be in the report that's on the Hyperloop Connected.
Yeah.
yeah, I was just thinking. So I think there's some more information in the report there as well, from some research organizations that you've worked with as well. Well, thank you very much to all our speakers today. Thank you very much for all the people attending. And I'll just hand over the word to Natalie to give us an outro and look forward what's next up.
Thank you very much for
hosting
this.
us.
Yeah, thank you very much for participating. Well, thank you very much to all let's say three speakers we had tonight. And also thank you to the audience for participating with the questions. So just a short outlook for the next seminar, which is already taking place in 1 week. We have two talks. One is by a company called POSCO, which is a steel company, and the other one will be hosted by Eurotube. So we're looking forward to those two interesting talks, and of course we also hope to again welcome most of you or all of you. And yeah, until then we wish you a nice week, a nice evening, and yeah, hopefully see you soon next week. And yeah, have a good week, and goodbye everyone. Thank you.
Goodbye.
Thank you, everyone. Bye bye.